Yeah, I present the paper Enabling Proofs of Data Replication and Retrievability in the Cloud. It's joint work with Frederik Armknecht from the University Mannheim and Ludovic Barman, who was a student in our labs, and my colleague at NEC Labs, Ghassan Karame. So it's in a framework of a joint project which aims to build a secure storage cloud. And now the scenario you all know of cloud storage. So users have data, users upload them to the cloud and are then at any time have the possibility to retrieve the data by sending a request, getting the data back, and we look at such kind of block or file-based storage as Dropbox, Google Drive, OneDrive are offering. A main concern of the users, which prevents them from adopting the cloud, and also corporate users, I will say a bit more later, is data loss. So in this list of the Cloud Security Alliance, data loss is up at number 2, so data breaches. Another concern, we are not looking at data breaches here, so we assume data can be encrypted and there's no functionality or sharing needed. But then data loss directly comes at number 2, and it is joined with malicious insider. And yeah, one solution which is well known in the cryptographic literature and security literature is a proof of retrievability, originally or sometimes also called proof of data possession. In a proof of retrievability, a user will send a challenge to the service provider, kind of asking, is my data still there? And then get back a response which gives him a proof that the data is still there. So, I mean, trivially, it could be that the user downloads his data and checks if it's there. But of course, the protocols try to do this very efficient. So how do they generally work? The user pre-processes the data before uploading. He applies some erasure coding so that he doesn't need to be concerned about every byte of the data. And then we'll add some tags, which are kind of homomorphic message authentication codes or homomorphic signatures of some blocks, and then stores all of those data at the service provider. And then he can issue a challenge asking for certain blocks. If they are still there, the service provider will sum up those blocks and the according tags. Then, because it's homomorphic, the service provider can aggregate all of it, send it back, and the user can check that this is indeed a response to his challenge. And it is a valid response based on his data. Yeah, I mentioned already you can do this based on homomorphic max, which is kind of A times X plus B. Those are rather quite efficient. You can also do it based on homomorphic signatures. Those protocols are a bit more expensive, but they have the advantage that you can get public auditing of a cloud storage provider. So then everyone would be able to verify the proof. Okay, what should it guarantee? Of course, such a protocol needs to be correct, meaning if the cloud is doing everything correct, the user will accept, and we have the other requirement of soundness or extractability, how it is then called for this specific case, which means that if the verifier accepts, so if the user from this short protocol gets, okay, my data is still there, then indeed the data should be extractable, and it's usually shown that an algorithm which can create the valid responses can be transformed into an extractor which can extract the file from the service provider. The adversary model we use is that the user is honest. Well, it's the user's data we are concerned of, and he will not corrupt his own data. And the service provider may be malicious, so we do not use a fully malicious model here, but adopt the rational adversary model, where the adversary's goal is to save cost. I mean, no one would do business with a fully malicious service or a service he doesn't trust, but on the other hand, we know all of those services are private for-profit entities, so they try to offer the service, of course, as cheap as possible, and we have learned that you cannot prove that security measures are really needed, so they might skip some of them and put the the data at risk, which would not be what the user wants. But yeah, there we come also already to one of the problems, namely the drawback of a POR is, well, if the user gets the notification, no, the data is not available anymore, he cannot do much more than panic. So it's too late, the data is already lost. What the user actually wants to know is that necessary security measures are in place, and well, how do you secure against data loss? You simply have a backup somewhere, so the user could have kind of 2 providers he uses and checks with the proof of retrievability with each, and if one is lost, he recovers it from the other provider and uploads it again to one provider. But then, of course, the user would do a lot of data management, which is not what we want. But, well, the providers are doing exactly the same. If they offer a high storage with a high durability, they replicate the data by themselves. And yeah, indeed, this is then what the user would like to know. Is my data really replicated? And we also hear this a lot when we talk to corporate customers who want to adopt storage. So what they are concerned of is that from this third-party service, they would like to know that they apply all the security measures which need to be in place. And this is certainly an obstacle, because with the in-house data center, they can easily check, but with the third party, this gets more difficult. And yeah, so this initial question, if my data is still there, rather transformed then into the question, is my data really sufficiently replicated as my contract with the service provider is saying? And yeah, now we learned a bit already how this proof of retrievability works. The question is, how can we apply it to multiple replicas in a standard way? Like if the replica are just exact copies of the original file, this is difficult or not possible, because it doesn't prove the existence. So if I query now the multiple replicas, because they are all the same, the service provider can answer them all just by having the original file. So this approach will not work. Another approach, already known for a while by Kurt Mohler et al., is the multi-replica PDP. And there the idea is that the replicas are encrypted copies of the file, which the service provider cannot replicate by himself, but the user has to first create the copies, encrypt them in a different way, and then upload all of them. And because then for the service provider, these are simply different files, you can run a proof of retrievability over every file, and then of course check that the file and the replicas are still available. We see some disadvantages with this method. First, we again put the user into the data management, into the one who is creating the replicas. This is a bit an unrealistic assumption, and it also puts cost on the user for uploading his data. several times, but as well to the provider, for whom also there's quite some cost associated to having enough bandwidth now to have maybe the 4-5 times the incoming data volume. So we used some of those numbers really to evaluate. So from Cloudflare, there are some data published what it costs for big providers to have incoming bandwidth. And yeah, based on this, we really can see there is cost associated to the upload. Another drawback certainly comes because it is restricting the business of the cloud provider. Well, if you look, for example, at Amazon S3 pricing, so Amazon offers the standard storage, which has very high durability. It's very highly replicated, and has the reduced redundancy storage, which might be even not replicated, and therefore offers just 99.99% guarantee that the data is not lost. And if you compare the prices, you see it's not so much more expensive to use standard storage, which clearly shows that for replicas, the amount charged to the user is much less than for the original file. So kind of the profit margin only goes to the original file, while the replicas are given much cheaper at the cost of the actual storage by the provider. And well, clearly customers wouldn't pay twice or 3 times the price if they want to have replicated, so this business model makes sense. But of course, this only works if the provider knows those are replicas. Like in the MR PDP, it could easily be that the user claims it's replicas because it's differently encrypted files, but it actually is not. So what we did is we come up with a generic model for such an MR POR, or we call it a POR2, proof of redundancy and proof of replication and retrievability, which extends the standard proof of retrievability. So we have, as in the standard retrievability, the protocols to store data and the protocol to challenge and verify the challenge, which we put together in a verify as one protocol. But the 2 new protocols we look at is first replicate. So this will come later when I explain our protocol. So replicate should enable the provider to replicate the data by himself. Or we have check replica, which would extend the MR PDP by enabling the provider to verify that the uploaded data are indeed replicas. The security definitions, again, as it's a proof of retrievability, we want data extractability, so we want to know the data is still there. And the second notion we created and defined is storage allocation, which guarantees that the provider really needs as much space as would be needed for the file and all the replicas. And well, as it is a rational adversary, then it only makes sense for him to store the replicas because the storage space is consumed in any case. Yeah, correct replication, again, for the MRPDP-like protocols. The definitions in detail you find in the paper. So then I come towards the protocol we designed, and which is called Mirror. So which asks the question, what needs to be done so that the service provider could replicate the data by himself? And of course, that's kind of a dilemma because well, we have this challenge response in the verify, and there we would like to find the cheating service provider who was not replicating but is now replicating on the fly. So this responding should be rather costly if you have not replicated before, which means the replication process needs to be associated with some cost, time-wise or computation-wise. On the other hand, for the store replicate, we of course want to have the costs rather low. So if we upload something, the service provider needs to replicate everything, but of course this should not take forever. So there needs to be a fine balance found between the cost high enough so that we can catch him during the challenge response, but low enough so that replication is possible. And the kind of primitive we use are cryptographic puzzles. So those are functions which consume a certain time to solve, and kind of two famous ones are out there. One is, given a value, find a pre-image according to a hash function. Well, this is very difficult to apply here. On the one hand, it's of course elegant, because you could have the data, and the pre-image of the data would be the replica, and you can easily, from the replica, create it back by hashing, while it takes a while to replicate it to find the pre-images. But to find pre-images, you would need to reduce the block size to a very few bits, and also you don't have homomorphic properties. So in the proof of retrievability, it will not going to be efficient. So we followed the second approach. There are those RSA-based puzzles. Now they are not related to the data directly, but we can combine them in a homomorphic way so that we keep all those properties. And this matrix gives an overview how we combine it. So we multiply it. From the puzzle, we extract some blinding factor, which basically is the solution of the puzzle, and multiply it to the data to generate one replica. So D11 to DNS is the file split into blocks, and the blocks split into sectors. And one sector is kind of like then the size of the RSA modulus. And yep, now it's turned out to be quite difficult to come up with the right parameters. So the basic RSA puzzle is saying you compute g to the x for very large x, so x is 2 to the L, modulo n, and how you do this, if you cannot factor n, is that you do a successive squaring modulo n, so you really have to compute it with this huge exponent. But if you know the factors of n, you of course have a shortcut, because you can apply modulo phi of n in the exponent, and then just have a standard exponentiation with a kind of 2000-bit exponent, while x could be much larger. However, it's difficult to apply it straightforward, because the exponents need to be very small. Like if you have 2000-bit exponents, replication of a 100 megabyte file is already taking several hours. So exponents have to be extremely small, but then of course you do not really have a good trapdoor, because then modulo phi of n, so if it's smaller than phi of n, there is no advantage for the user. So we looked for another way, and how we could involve several of those puzzle solutions to obtain one blinding factor. And well, if you multiply several of those puzzle solutions together, you kind of end up with a structure very similar to a linear shift register, just transformed into the multiplication domain. So we have kind of the puzzle solutions with the exponents S1, S2, S3 to S8. For the example of a register of length 8, the register is given by the coefficients C1 to C8. And now what you do is you take the first cell, raise it to the power C1, then multiply it to the second cell, raised to the power C2, and so on, and multiply everything up and get the next blinding factor G to the S9. So this is kind of LFSR, which is transformed in the multiplicative domain. And you can have the according shift registers for the exponents. And there it's really a standard shift register with multiplying the coefficients and adding up. So this is much faster to compute the exponents, but you could give out the public one, which is expensive to compute for the blinding factors. And it is not possible to transform the public one into the secret one. So now, besides that you have to multiply in the public one and only do additions in the secret one, we could apply another kind of another trapdoor. If we choose a shift polynomial which is not primitive, so means that it has some redundancy, and also the sequence of blinding factors, of course, will not have the full cycle length it could have, but a shorter one. So it produces kind of a sequence which could be already produced by a much shorter polynomial. So exactly this we apply here. We use in the public LSFR a multiple of the feedback polynomial of the secret one. So the LSFR gets much longer, but it again cannot be transformed back because it's not possible to factorize this polynomial as we are in an RSA group and cannot compute inverses there. So in fact, with the parameters we choose, the secret one just needs to be length 2, and the public one can be up to length 15 or longer. So we get quite a good difference in the effort it takes to compute the blinding factors if you know the factorization, and if you compute the blinding factors if you don't know. Now this is exactly what we do here, and we use two pairs of shift registers, one forward, computing the blinding factors from the first to the last, and one backward, computing them from the last to the first, which guarantees that for every, so if you try just to get one block somewhere in the middle, you have to compute all of them, all of the blinding factors before in the one chain and all of them which follow afterwards in the second chain. So you kind of have to compute always the same amount of blinding factors, no matter which position you look at. Yes, the parameter choices I mentioned. So the RSR modulus 2000 bit. The POR usually takes 40 challenges, so that's not dependent on the file size because we apply the erasure code before. So there's the variability. And then just use length 2 LFSR for the private and a length 15 for the public, and the exponent in the private one is around 70 bit. 70 bit, there it shows that the cost for computing, for answering this challenge for the service provider is exactly the price which it would cost to store a file of the according size on Amazon S3. So there we have the same cost for answering the challenge if you don't have replicated as it would be to simply store the replica. So if you frequently challenge the length of 70 would be well suitable. Besides that, it's then the same cost, of course. There is the timing. So usually on the right side, you see it takes around 2 seconds for the server to answer a replica, but if the server has not stored the replica, it takes him at least 3 seconds, and this can be very well noticed. Creating a replica is kind of reasonable, so times go into the few hundred seconds. And then I conclude. So we introduced this proof of replication retrievability as a new notion extending the standard POR, and I think bringing it a bit more towards realistic settings. We have developed this solution mirror, and we have there a new puzzle, a new asymmetric tool built on LSFR. So this we haven't seen before, that you construct such a public LFSR, which has redundancy because the polynomial is not primitive, but you cannot transform it back to the short polynomial, which we also think could have many more applications. And this all is building block for the vision of having these transparent cloud services, which you can verify and check as if you would have your IT in-house. Okay, thanks.
Great, and if you have a question, please come up to the mic and state your name and affiliation.
Hi, Greg Zaverucho, Microsoft. So the gap between the honest cloud server and the cheating one is 1 second. Like in your parameters, it was 2 seconds to do it honestly.
Yes.
So
I think it's around 1 second. Yeah.
Can you talk about the trade-offs if you wanted to make that larger?
Well, the thing is, if you want to make it larger now, for cheating this protocol, there's a challenge which just varies limited blocks. And so the cloud provider only needs to compute those limited blocks. Now, if you make those few blocks more expensive, there is the risk that at the same time you also increase the replication cost. So it's kind of, I think you find more analysis in the paper. So this is also one idea which we have in where is the matrix? Here. So for replication, you need to compute all the blinding factors. So what you ideally want is that even if you just want to give back one block as an answer, you should need to compute all the blinding factors. Because then, so if you increase the number of blinding factors you need to answer one block, this does not cost you more for replication, but this increases the cost for answering the challenge, the one block. So on this, you could play. But kind of the parameters I've shown is the optimal spot we have found.
Okay, thanks.
I actually have one question about systematizing this work, turning it into an actual system. So very few cloud providers, storage providers also compute, right? Many may have a compute node, but there's associated costs with those things. And one of the dominant costs is actually doing gets. So would it actually, is this economically viable, or does it make more sense to just like compute a MAC over the data and do one get?
So I think, there needs to be some computation simply to manage all this storage. So you don't need a full-blown EC2 for sure. But my guess or my hope is that there will be more storage also available, more computation in the storage clouds available, also because there is simply more transparency requested by the users.
I'm unaware of any cloud provider that would adopt a PDP or POR scheme because it somehow admits that they're being dishonest, right? I think they would much rather just say like, yeah, we'll provide 9 nines and we'll call it a day.
Yes. we have to see, maybe not in this pure form. I would expect some maybe hybrid things, some
like a third-party service,
kind of
maybe.
POR ideas, but some secure hardware guarantees. So some nice combination of it, I would in the end expect.
Great. Reza, please.
Reza Kutmola, New Jersey Institute of Technology. I don't have a question, just a comment. So I'm one of the authors of that paper MRPDP that you cite,
Yes.
published in 2008. Just wanted to let you know that we actually had a follow-up work after that in 2013, which does something very similar to what you're doing, shifting the burden from the client to the cloud provider for creating replicas, especially when some of those replicas fail and they need to be recreated. It's somewhat similar. We don't call it blinding, we call it masking. And I don't know if you're aware of it, you don't cite it. So this was in 2013. So I can send you the point.
If you send it to me, fine,
Yeah.
we are happy to look into it.
Thanks.
Thanks.
Great. Let's thank our speaker one more time.